9b part 2 problems 50, 60, and 78. Let's take a look. If the valence atomic orbitals of an atom are sp hybridized, how many unhybridized p orbitals are remained in the valence shell? Okay, so this is actually pretty easy. So when we talk about s, here we go, there we go. We have s, whether it's like 2s, and then you have 2p, like this. If I have sp hybridized, this might be something like beryllium, would look like this. And then we would promote one of those up to this, so that over here then what would happen is I would have an S and a P like this, and then what would be left over? Then the 2p would just have two orbitals that are empty, but those two would look like that. So if I promote an electron to an empty orbital, then whatever I have left over would be the unhybridized p orbitals. So these here are unhybridized. What kind of B is that? Okay, unhybridized p orbitals remaining in the valence shell. So that answers that question right there. How many sigma and pi bonds are generally part of a triple bond? So if we have a triple bond, something like nitrogen, like this, then I have this one right here. The middle one is the sigma bond. Okay, so that's the sigma bond. The two here and here represent other planes of side-by-side bonding instead of end-on-end. So the sigma bond is end-on-end, and then the other two are pi bonds. So I have two pi bonds that are side on side. It's tough to explain, but I'm going to show you in 1 second here. I'm going to flip past this. It says, how do multiple bonds introduce rigidity into a molecule? So let's take a quick look. Well, here, let me go down and just give a quick answer to this. How do multiple bonds introduce rigidity? So if I have a carbon and it's bonded to one oxygen that's then bonded obviously to a hydrogen. I have another one that's bonded to a hydrogen like this, but I have a double bond to another carbon and hydrogen and oxygen and hydrogen. So I'm just going to put this as, it's called a hydroxyl group. It's the OH, so that we know what we're talking about, like this. Notice here, because I have a double bond, that I have like, notice that I can have the OH across from the OHs, like they're diagonal, or I can have them on the same side, like this. And whichever way I put the OH, it stays like this, because this double bond right here will not allow the carbon and carbon to rotate around like that. Okay, it's difficult to explain without showing you an actual model, because this all happens in 3D. But if I have a double bond here, then what happens is that the OH on top here and the OH on top here are locked into position, and this is called cis, where it is like across from each other. If I have them where they're diagonal, that's called trans. Okay, so next is cis, diagonal is trans. You don't have to write that down whatsoever, but what I'm talking about though is the double bond locks the other part of the molecule into position and will not let it rotate. Like if I have hydrogen, hydroxyl, and hydrogen here, then with a single bond here, and I have hydroxyl, hydrogen, and hydrogen, I can rotate these here so that they can be in any configuration. Because this bond right here, that single bond, it doesn't lock the carbon and carbon into a stable position. It allows for rotation. So that's how rigidity of a multiple bond actually causes a molecule to be one way or another. So take a look at this. This is really confusing. So this right here would be our sigma bond right there. That's end on end. That's the two lobes that are, one lobe comes from one carbon, one lobe comes from one oxygen, and they overlap in the middle, and this is the strongest overlap. That's why it's called a sigma bond. The other bonds are the ones where you see up here like this, and the overlap happens side to side. Okay, now this is all still part, this is a double bond here because this is one lobe of the same P, like this. Let me show you what I mean by that, because I'm using only red here, and what I should do is use a different color to show you that what I have is a dumbbell-shaped P and a dumbbell-shaped P. And this is, I know this looks strange, but this is what that looks like. One of them is sigma, and the other one then would be pi. Okay? And the sigma is always the end-to-end. It's always the first bond that happens because the two lobes are reaching out towards each other and they overlap in that way. The other two lobes, the ones I have in black here, end up going side by side like this. So that is two bonds I'm showing you, the sigma bond and only one pi bond. Well, what happens if we have a triple bond? Well, a triple bond then would be a sigma first, just like you see here, sigma, and then here is one pi bond, happens here and here, that's one, and then a third one happens, I don't know if you can see it, it's kind of, because it's three-dimensional, it's kind of like it's back behind there. So here you would have something where you have carbon and you have three bonds, and one of them would be one of the pi bonds, the other one is the other pi bond, and then the middle one is the sigma bond, and that's because you have like that, maybe hydrogen and hydrogen. So the black is sigma, one pi bond is green, one pi bond is red. Notice that red pi bond has two parts. It's got a top part and a bottom part. That's because one orbital of a P for a P sublevel has a shape like a dumbbell, like that. Both lobes are part of the same orbital. So we see one orbital, like if I put this as like the right orbital or the left orbital, okay, then we would have like the right orbital here and the left orbital here. Okay, and it matches up with the right orbital of this one and the left orbital of this one. Okay, so it looks like there's two bonds there. There's not. It's only one bond because that shape has two lobes. Okay, that's why. I don't know if that makes sense. Let's move on. I feel like I'm spending a lot of time here. Why is the anti-bonding molecular orbital of H2 at higher energy than the electron in a hydrogen atom? Okay, so one hydrogen atom looks like this. It's got the one S like that. The other hydrogen atom is over here like this. It's got the one S like that. These two red and black orbitals are coming together so that over here it looks more like this. Oops. Let's keep it the same. One of them goes down and one of them goes up. Okay? This one goes up, the red goes up, the black goes down. Okay? One of them, by going down, the two electrons end up in the bottom orbital. Okay? This is our bonding orbital, and this is our anti-bonding orbital. So the one that's higher is at a higher energy. And that means that it takes energy to put electrons in there. And if we have a higher energy there and we have too many electrons, then that breaks up the bond with the one that's below it, which is kind of strange, but it destabilizes. So the more electrons I put up here, the more unstabilized my bond is between whatever two elements I have. So that's why you saw in 9.6 or 9.7 that, I think it's 9.7, you see the He2 bond does not exist. And that's because He has two electrons in the 1s, and that means that we have two electrons in the bonding orbital, the molecular bonding orbital. By the way, a molecular orbital is very similar to an atomic orbital. but we have 2 in the anti-bonding. And because that there's 2 here, it means the bond doesn't even really happen. Okay, it doesn't even really happen because it's just not stable. This kind of cancels the 2 on the top anti-bonding, kind of cancels them all out. Does the Pauli exclusion principle apply to molecular orbitals? Yeah, absolutely it does. So when we go from, here's what the Pauli exclusion principle with, if I'm using my hydrogen, I can use the same one now to explain. If I have 2 atomic, here they are atomic orbitals because they're not interacting with each other. The hydrogen 1, hydrogen 2 are not interacting with each other. As soon as they do interact with each other, the only thing that happens is the position of one of them goes down and the position of the other one goes up. They both hold 2 electrons, maximum of 2 electrons. Okay, they follow the same rules as atomic orbitals do. The only difference is that their placement is basically in between, like positioned between the 2 atoms' nuclear, like nuclear positions, or the nucleus of both atoms. So now I have these 2 electrons are attracted to that nucleus and attracted to that nucleus, and that's why it holds the bond together. But as soon as you start to put electrons up top in the anti-bonding orbital, because these 2, first of all, you have to understand, I have one orbital here and one orbital here, and one of them goes down and the other one goes up because the other one has to go somewhere. We don't combine the 2 orbitals into one orbital. Okay, the orbitals are the same, they just one moves into a more stable position and the other one moves to a less stable position. They say in the book that the atomic orbitals are actually conserved, and that confuses the poop out of people. And what it actually means is that the atomic orbitals are still there, they're just now in between the 2 atoms. And they follow the same rules, can only hold 2 electrons. They must spin in opposite directions, those electrons. Like all the same rules for the Pauli exclusion principle that talked about the 4 quantum numbers. I know that we didn't spend much time on that, but still all the same rules apply. Atomic orbitals equal molecular orbitals. The only difference is where they're positioned. If 2 p orbitals of one atom combine with 2 p orbitals of another atom, how many molecular orbitals result? That's easy, it's 4. I'm answering the same question as I did before. We conserve the orbitals. If I have 2 and 2, then I simply add them together. I don't know what I was going to write there. I think I was going to do this, and I know that's not very helpful. So if I have 2 atomic orbitals from one atom and 2 from the other orbital, other atom, then I have 4 molecular orbitals. 2 of them will be bonding. Okay, so 4 equals 2 that are bonding and 2 that are anti-bonding. That's the better way to say it. That if you put electrons in these anti-bonding orbitals, they will disrupt the bond. So 2 promote a bond and 2 disrupt the bond. Keep moving. 78, consider the following molecule, PF4Cl. I love this. P, these 2 are group 7. F and Cl are group 7. They're also a little bit higher in electronegativity, so automatically P is what I'm going with. Now, this doesn't work because I only have single electrons. I only have 3 single electrons, but I got 5 things bonded to P. I know I have 5 single electrons, and P is in the third period, which means that it can do this. That means it's going to bond to F, 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 Cl. Okay, so what's the molecular geometry? Is 1, 2, 3, 4, 5. That is electron domain geometry, is trigonal, bipyramidal. I hope you guys are starting to figure these out and starting to get used to using these names. That means the molecular geometry then, because there are no lone pairs, molecular geometry is also trigonal bipyramidal. Okay? So now that we know that, which would you expect to produce a larger electron domain? A PF or a PC bond, and why? Well, that's actually pretty simple. PF, whatever P is for electronegativity, the F is larger because it's the largest one. It's going to pull the electrons towards that F, which gives it a larger domain. More electrons means larger domain, or electrons closer to that atom means larger domain. So the PF is going to be larger, and the reason is because of the larger electronegativity. Okay, that says electronegativity. That's pretty easy, actually. So that makes sense that the fluorine will pull more electrons to itself because it's got the largest electronegativity. So the PCl is not going to be nearly as big. Okay. Ooh. Oh, I thought there was a B and a C. All right. Well, if there's not, screw it. I forgot. Maybe. Yeah, I don't know. All right. Good. That's something different. Thanks for paying attention.